given a space X, vector space, points of X sufficiently close to A. This is not a terribly mathematically precise, but it gives you a kind of qualitative idea of what a neighborhood is. It's containing all the points of X that are sufficiently close. That's a little vague to A. Okay. Actually, from this definition, an open ball around A is a neighborhood. Right? I mean, this, since an open ball centered at A, radius delta, is a subset of itself, if you will. Subspace of itself. Okay, so we can say that that is an open ball given the delta greater than 0. Okay, an open ball around A is a neighborhood. Okay? Is a neighborhood. Now, since the underlying theme of all this is to characterize or define continuity at a point in different ways, the next thing I'm going to do is to give a fourth definition of a function being continuous at a point using, guess what? Neighborhoods. Okay. And the idea is that all of these definitions that I'm giving you they're all equivalent. Because they're all really saying the same things in slightly different language, couched in different language. So let's give another definition now. Here's a theorem. I'm saying these as theorems, which of course I'm not proving, but I think as long as we kind of get the idea, we understand what they're saying, it's good enough. So supposing I have a function which is mapping x, this is a metric space, call it x, is metric d, into another metric space y, with its metric d prime. Then f is continuous at a point A in X, if and only if, for every neighborhood, I'm going to abbreviate neighborhood, for every neighborhood n of f of a, and I'll draw a picture of this. There exists a corresponding neighborhood n. Of A, is that right? Yes. F is continuous at point A if for every neighborhood n of the image f of A, there exists a corresponding neighborhood n of A. And what I'm saying is that the image of n is contained in M, or equivalently, n is contained in the pre-image. I'm going to draw a picture of this, because this might be a little bit. Let's here is, again, remember what I said, every definition of continuity has to essentially convey the same meaning. So we still, even in this new vocabulary, this new language, it must still be saying exactly what we've said before, that under the mapping F, points that are close should be sent into points that are close. So let's just see if this fancy language really supports that, is really saying that. Let me see if I can draw a picture of this. So supposing, okay, this is the domain space, and here is the image space. Okay, so here's the mapping F. Okay, that's taking X into Y. All right. Here's a point A in X, and now what does a neighborhood? So a neighborhood of A contains an open ball centered at A, so there's maybe some radius delta there. Okay, and a neighborhood M of F of A. Say this. I should draw this a little larger. Okay. Can you see this? In here is F of A, radius epsilon. Okay, and so this is an open ball centered at A, radius delta. This is an open ball centered at F of A, radius epsilon. Okay. So what we're saying is that if this function F is continuous, then for every neighborhood of F of A, which essentially is saying points close to F of A. Remember, the open ball around F of A is a neighborhood too. For every neighborhood, there's a corresponding neighborhood around A. So it's another way of characterizing or describing or stating that points that are close here in the image space came from points that were close in the domain space. Okay. This could also be stated in the following way. I could say that F is a mapping of X metric space X with metric D into metric space Y with metric D prime. Then F is continuous at a point at A in X, if and only if for every neighborhood M of F of A, every neighborhood in the image space, the pre-image of M is a neighborhood of A in the domain space. The pre-image is a neighborhood of A. So this is, in a couple of minutes, I'm going to be defining an open set. And this theorem will translate into essentially pre-image of open sets is open, and that characterizes a continuous function. So, but all of these definitions really are equivalent. Okay. Just a little more vocabulary here. I did want to say this, that in a metric space, the open ball B centered in A radius delta is a neighborhood of each of its points. Neighborhood of each of its points. Okay, that's this. Okay. I want to define now when I mean by an open set. I'm going to need that. So I'm going to say a subset O of a metric space is said to be open excellent, defining open if O is a neighborhood of each of its points, is a neighborhood of each of its points. I'm going to start this one. Let's just look at these two statements. A subset of a metric space is open if it's a neighborhood of each of its points. In a metric space, the open ball is the neighborhood of each of its points. So, how can what can I conclude from these two statements? That an open ball in a metric space is what kind of a set? Yeah, is open. So these two statements imply that an open ball is an open set. What's the most familiar one that you've seen? I mean, from Calc 1, just function of real variable defined on R1, an open interval around A is an open set, and it's an open ball. Let's say the radius delta. And then we have a theorem. I'm not proving any of these theorems. These results. A subset O of a metric space X metric P is an open set if and only if it is a union of open balls. If it is a union of open balls, and okay. And now, one more definition of continuity using open sets. You see how, if you look at the way we've been building this up, we started with the idea of a metric, and then we went from the metric, we used the metric to define what we call the open balls, then we went to neighborhoods, and now we're going to open sets. And in each case, we're going to be coming up with a new definition of continuity, but it's not really new, it's just the same meaning of continuity expressed in terms of these different kinds of objects. Okay? Again, points that are close are mapped into points that are close. That's essentially the notion of continuity that never changes. So one more definition of continuity is if you didn't have enough.